So you have a capacitor, you let it discharge, and we can look at how the charge varies with time. Now there are three equations that we can think about. First of all, we know that the current is going to be equal to minus dq by dt. Effectively, the current going through this is going to be equal to the rate of flow of charge, and that changes with time. We also know that Q is equal to CV, so the capacitor, the charge stored is equal to the capacitance times the potential difference across it, and also we know that V is equal to I times R, because that's just one of our kind of basic equations. So what we can do is I can replace V with IR from over here. So I'm going to replace this term here, and I can then say that Q is equal to C times IR. The next thing I can do here is I can replace this I term over here with this term up here, because we know that I is equal to minus dq by dt, and therefore we can say that Q is equal to minus C times dq by dt times by R. It's looking a little bit messy at the moment, so I'm going to write this as Q is equal to minus RC dq by dt. I'm going to bring all of the Q terms together, and if I do that, just bear with me, but what we can say is that we get something like this. So effectively, I've said that 1 over Q dq, I've taken minus RC over to this side, taken the dt up here, so hopefully you can just work that through. But this is what we get. What we can then do is we can integrate by parts. So we can say that the integral of this, so 1 over Q dq, we integrate that. 1 over RC is just a constant, got nothing to do with time, and therefore we can integrate effectively 1 times dt. If I do that, what we get, and I'm just going to swap these things over, we get ln Q, which is the integral of 1 over Q, is equal to minus 1 over RC times time, which is 1 over RC, effectively 1 integrated is t, and then we add this to our constant k. If I raise both sides to the power of e, we can say that e ln Q is equal to Q, and that's equal e to the effectively minus 1 times t over RC is equal to minus t over RC times e to the k. Okay, so this is the way we've done that. Again, hopefully that should make sense. We need to think about solving to find out what this constant, this kind of constant in it, this integration constant is. And what we know is that at time equals 0, the charge is equal to the initial charge, which is Q naught. So if we put this in, we find that at time 0, Q naught is equal to e to the 0, which is just 1, times by e to the k, which means that our constant e to the k is equal to Q naught. And we can then put this back into this equation up here to find this at any time Q is equal to Q naught e to the minus t over RC. And that's why capacitors have this exponential function in here. That's why the constant here, RC, comes about, this time constant. And yeah, that's it. Hopefully that mathematics makes sense. You don't need to recall it, but I think it's useful to see where this equation, which not just works for the charge, but also works for the potential difference and the current, actually comes from.